Hello everyone. My name is Hui Song. I come from Institute of Computer Technology, Chinese Academic of Sciences. Today I will introduce our work called MCCBench, a C10M benchmark oriented to interactive network services. The interactive network services penetrate into our life widely, such as smart home and social networking. Billions of connected terminals have sparked the ever-increasing concurrency. Due to the social focus, the traffic has shown fluctuating in force. The multiple service demands are different. In other words, the requests have multiple priorities. So a suitable benchmark for interactive network services needs to evaluate the server ability on handling high concurrency bursts and multi-priority requests. The high concurrency motivates the C10M trend to save the hardware investment. For accurate evaluation on server, it's better to measure the server-side latency. However, there are no open source benchmarks satisfying all the requirements yet. We studied the existing benchmark tools showing in the table they have not achieved the benchmark requirements and economical cost at the same time. And it's also lacking toward measuring the server-side response latency. We are promoted to develop a tool set implementing the benchmark methodology as a typical study case. The metrics involved in the server performance are diverse and interrelated. So the benchmarking are hard to be represented by workload with finite category. As the common feature of the multiple interactive services can be defined abstractly by a set of methods. We design MCCBench as a measurement standard which realize the test methodology definition in workload, service framework, and performance evaluation. First, we define the workload pattern. The request of each long-lived connection arrives at the server at fixed interval E. Then the RPS queue is computed. To measure the server ability in handling bursts, queue requests are sent to the server in several bursts. Generally, the burst is modified in proportion to concurrency. A burst will be sent within the limited time to ensure the aggregated pressure. Multiple priority requests are evenly distributed in each burst. The priority label are predefined field inside the request payload. Second, the service framework is designed to identify and schedule the multi-priority request. We chose querying in-memory database in key-value mode by default. It extracts the content in request payload for custom computation. Each request queries the database with custom read or write operation. The response format can also be configured. Finally, considering the good user experience, the performance evaluation are defined. We evaluate the server-side tail latency under the given concurrency and the maximum concurrency under the tail latency threshold. For the MCCBench first implementation case, we pick IoT service as it's one of the typical interactive networks. Taking the smart appliance as a case, we show the IoT features. Under the massive long-lived concurrency, the requests are classified to 5% query requests, standing for high priority and demanding responses, and the remaining 95% heartbeat for connections keep alive, which don't need a response, and stand for low priority. The request payload carries the IoT label representing the priority and the device information. The heartbeat packet frequency of a connection is usually once a minute. And since the average human reaction speed, the tail latency threshold is best within 50 milliseconds. for good user experience. We have developed and integrated an open source toolset MCCBench IoT to represent the benchmarking on a typical IoT scenario. The MCCBench IoT toolset is improved on a baseline, including a load generator, a service application, and a monitor. The MCC generates burst and multi-priority requests. LTP server is an IoT service with Redis query. HT monitor measures the server-side latency in real time through switch mirroring the full traffic. For the performance and the IoT configuration, we have optimized the baseline to be MCCBench IoT toolset. For MCC, we have improved the concurrency to over 10 million on single node, which over 10 core scalability. We also developed the multi-node to realize a distributed system. We optimize the synchronization of the cluster nodes so that the bursts produced by multiple nodes are destined to servers synchronously and aggregated. We optimize the LTP server performance by adopting zero-copy algorithm based on the user-level TCP stack, QStack. A log-free distribution framework DW is developed on multi-thread for scheduling requests of multi-priority. So it supports over 10 concurrent connections on a single node. The DW consists of fully interconnect queues and connect with multiple Redis processes on server. Each request can query the Redis process through DW for read or write operation. In order to monitor the large-scale system, we also make the multi-node scalability on HT monitor. It regularly collects the test data of monitor nodes and makes the interval static. The testbed machine and the topology is displayed in the picture. We give several experiments, including the tail latency and concurrency, to evaluate the MCCBench IoT system performance. We configure the parameters according to the statistical data of the smart appliance kit. We take the 99th percentile response latency as the tail latency, and we tested the tail latency under hundreds of thousands to million of concurrency to prove the concurrency scalability. It successfully shows the tail latency with 10.2 million concurrent connections on a single server. We also test the concurrency upper limit up to 12 million and the tail threshold to be 50 milliseconds. In proof of the concurrency extension, MCCBench has been applied to the service system built by tens of nodes, measuring over 300 million concurrent connections. The tail latency are also tested at about 3 milliseconds. In conclusion, we have presented MCCBench as the C10M benchmark for the interactive network services. It provides definition methodology in load generation, service framework, and performance evaluation. A toolset MCCBench IoT is developed for implementation and case study. It represents the IoT scenario and supports C10M concurrency. It can scale to cluster with over 300 million concurrency. In the future, we plan to expand the MCCBench workload generation with various statistical distribution and the MCCBench toolset to non-IoT services. That's my report. Thank you.